For a bit of a bonus lecture, I want to talk about carbon-13 DEPT called depth NMR, and also briefly about two-dimensional NMR. The reason I want to include this lecture is because the ACS final exam often includes carbon-13 NMR spectra alongside of or in place of hydrogen NMR spectra. So I want to make sure that should that appear on the ACS exam this year, that you guys are prepared. So carbon-13 having an odd mass and therefore a non-zero spin, carbon has 6 protons and 7 neutrons. That means that all 6 protons will pair up in pairs and will have 0 spin, and 6 of the 7 neutrons will pair up in pairs and have 0 spin, but there will be one unpaired neutron with spin of a half, and so carbon-13's nucleus will have a nuclear spin and therefore make it sensitive to NMR effects. Something called the gyromagnetic ratio is what makes carbon-13 NMR a little bit different from hydrogen NMR. Now, generally speaking, the greater the magnetic field that the nucleus is placed in, the higher the frequency. And there's a relationship between that. Usually it's a linear relationship, and there's some slope associated with that. For example, as you increase the magnetic field, the frequency of precession increases at this rate for hydrogen. But for carbon-13, as you increase the magnetic field, the frequency of precession increases much less dramatically. That slope is called the gyromagnetic ratio. That comes from quantum mechanics. But regardless, the gyromagnetic ratio for carbon-13 is much smaller than that of hydrogen. It's 75% less than that of a proton, which means that at any given magnetic field strength, carbon-13 is much less sensitive to that magnetic field. Lower precession frequencies are much more difficult to detect. For example, in a magnet where a bare proton would precess at 100 megahertz, the carbon-13 nuclei would precess at 25 megahertz. Additionally, carbon-13 is less abundant than hydrogen. So, for example, we know that 1% of all carbon is carbon-13. So if we've got 100 carbon atoms in our sample, only one of them will be NMR active. That means the signal is also much quieter. When you combine those two things, the less sensitive gyromagnetic ratio and the lower abundance of carbon-13, the carbon-13 nuclei are only about 1/10,000th as receptive to NMR effects as protons. So it's a much more difficult spectrum to acquire. It takes a lot longer because you have to take more scans so that you can acquire more signals and add them together to get a more clear spectrum. Carbon-13 and protons will couple with one another, and they have a very large coupling constant, that J coupling, constant with each other, that's in the range of 85 to 250 hertz. Now, those are huge numbers. Remember that for sp3 hydrogen neighbors, they split at 7 hertz. Carbon-13 and neighboring protons split from 85 to 250 hertz. So these make spectra really complex. So let's take a look at what these kind of complex spectra look like. Here's the carbon-13 spectrum of ethanol. Now, clearly this is not complex. What's going on here? Where is the coupling between carbon and hydrogen? We have 2 signals, so we're looking at 2 carbons. We have 2 signals, so that makes sense. But these carbons are neighbors, so we would think that they would split each other the same way that carbons and hydrogens would split each other, or that neighboring hydrogens would split each other. We know why we've got 2 signals, because we've got 2 different types of carbons. They're different because they're in different chemical environments. But what do these signals mean? Notice our range of ppm is also extremely different. In proton NMR, we went from about 0 relative to TMS to 10, maybe up to 12 for carboxylic acids. But for carbon 13, the spectra can go all the way from 0 to 200 and beyond. So, where's the coupling between C and H? That is actually removed by the computer. Like I said, the coupling between carbons and hydrogens are really, really complex and they're difficult to track. So we use software to simply remove those coupling signals, and it cleans up the spectrum tremendously. So that's why we don't see the carbons and the hydrogens coupling. We just remove it. It's not that they're not coupling, we just don't see it on the spectrum. We use a computer to remove that. Now, why don't carbon nuclei split each other? These carbons are right next to each other, and so we'd expect them to split each other. In fact, that might be very useful. We could tell how many carbons each carbon is next to by the splitting pattern. So, whereas that would be very useful, unfortunately, it doesn't happen because the likelihood of having two carbon 13 nuclei right next to each other on the molecule is very small. If both of these carbons were carbon 13, they certainly would couple with each other and we would see splitting. But that only happens a very, 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 very low percentage of the molecules in our sample, such that the signal is so faint that we don't really see it on the spectrum. Generally speaking, we might have one of these be carbon 13 and the other one would be a carbon 12, or vice versa. The other one would be carbon 12 and the first one would be carbon 13. Since carbon 12 is not NMR active, it doesn't show up. It doesn't interact with carbon 13. It doesn't split with carbon 13 because it doesn't have a nuclear spin to split it with. So this spectrum of ethanol basically tells us that we've got two types of carbons, that is to say carbons in two different chemical environments. The solvent that we use in NMR is often CDCl3. It's a deuterated chloroform. It's chloroform with a deuterium replacing a hydrogen. Since deuterium will couple with carbon, anytime carbon is carbon 13, a deuterium will couple with it because remember, deuterium has a spin quantum number of 1. We end up with getting a triplet with 3 equal intensities due to the possible number of spin states. Remember, we said that 2 times I plus 1 gives us the possible number of states, and deuterium with an I of 1 means that we have 3 possible states, basically plus 1, 0, and negative 1 with respect to the external magnetic field. That basically gets us a triplet. And so since we take the spectrum in CDCl3, you will often see this triplet occurring at around 77 ppm. Right now, you don't see it there. It's probably been removed from the spectrum. But in the event that you ever do see it, that's all it is. It's just solvent. You don't need to worry about that. Here are the ranges of carbon 13 shifts. Remember, in proton NMR, we looked at all the different types of protons from primary to secondary to tertiary to methyl ketone to aromatic to acetylenic to alcohols to amines to aldehydes to carboxylic acids. We looked at all those ranges where they would shift in ppm relative to TMS. Here are those types of shifts for carbon. We've got ketone carbons, aldehyde carbons, carboxylic acids and ester carbons, aromatic ring carbons, normal carbon-carbon alkenes. We've got carbons bearing an alcohol, carbons bearing a halogen, carbons bearing a nitrogen, carbons that only are aliphatic, that only have other carbons or hydrogens on them, methyl ketone carbons, carbons adjacent to a carbon or carbonyl. Here's a secondary carbon, here's a primary carbon. This one up here was a tertiary carbon. And all of these have an associated chemical shift, a range in which these carbons often appear. Again, basically from 0 or around 10 all the way up to 200 and beyond. Now, this is fine. If you want to memorize this, that's fine. I'm not going to hold you against that. But this table can be dramatically simplified over here in that there are basically only 4 different types of carbons that you will encounter. Carbons that are only single bonded to other carbons will show up anywhere from 0 to 50 ppm. Carbons that are single bonded to an oxygen will show up between 50 and 100 ppm. Carbons that are double bonded to other carbons show up between 100 and 150, and carbons that are double bonded to an oxygen show up from 150 to 200. This simplification is surprisingly sufficient, and for the most part in this lecture, we're just going to be following this scheme. We can look at which peaks show up in which of these ranges, and from that we'll determine how many of each type of these carbons we have. If you want a visual description of these ranges, again, ranging from 0, where TMS is by default, all the way up to 200 and beyond, we go from primary to secondary to halogen to tertiary to quaternary to carbons bearing an oxygen to triple bonds to double bonds to nitriles to carboxylic acids and esters, and then to ketones and aldehydes. Generally speaking, you see methyl, secondary with an X, tertiary, quaternary, carbon with an O, all of the pi type carbons, and then finally aldehydes and carboxylic acids, ketones and esters, the carbonyl compounds. But again, just for the sake of simplicity, for the most part, all you need is this. All you need are these 4 ranges and the corresponding types of bonds that our carbon has. So let's take a look at this sample spectrum here. Let's think about our 4 ranges for our carbon. We've got one peak between 0 and 50. That is a carbon that only has single bonding carbons on it. We've got nothing from 50 to 100. So we have no carbons that are single bonded to oxygens. We have 2 peaks between 100 and 150, which means we have 2 carbons that have double bonds to other carbons. And then we have 1 peak at 200, which would be a carbon that is double bonded to an O. So again, at 26 ppm, that's a downfield single bonded carbon. It's so far downfield that we're probably going to assume that it's a primary carbon, therefore a methyl. We've got 2 carbons that are double bonded. Now, since we've got 2 carbons that are double bonded to carbons, it makes sense that those are probably attached to each other. And then we've got this guy up here, which is our C double bond O, probably a ketone or an aldehyde because it's up so high. And here's our structure. This is called methyl vinyl ketone. It's a ketone with a methyl on one side and a vinyl group on the other side. This is exactly what we would expect. This carbon that's only got single bonds to carbon and it's a primary carbon, that is going to be our 26 ppm peak. The 2 carbons that are double bonded, those are going to be at 137 and 129. Again, the one that's closer to the carbonyl is probably going to be the more downfield one. And then we've got our carbonyl carbon, our C double bond O. That's going to be the farthest downfield at 200. Now, that is much simpler than the proton spectrum would be. If we were to look at the proton spectrum, we'd have a singlet from our methyl, but we would have complex splitting with our vinyl group because this hydrogen here would split as a doublet with the cis neighbor and as another doublet with the trans neighbor. So we'd get a doublet of doublets from this pattern here. So we'd have a singlet and a doublet of doublets. That might be more difficult to interpret. Now, it's even better if you can combine the two. If you can take an NMR spectrum using proton and NMR spectrum using carbon-13 and look at them together, you now have 2 complementary pieces of information. It not only tells you what types of hydrogens you have and what they're next to, it also tells you now what kind of carbons we have and what they are attached to. Remember, we can't really tell what carbons are next to because the carbons are very unlikely to have another carbon-13 neighbor. Let's try this spectrum. This is C4H10O. We can get this type of a formula from a mass spectrometry experiment, find the molecular weight, rule out any other isotopes. From that, determine what our carbons and hydrogen ratio is. This is C4H10, which means that it has 0 index of unsaturation. Our carbon spectrum is very simple. We only have 2 signals. Now, this is very interesting because we have 4 carbons, but we only have 2 signals. When you see that, you want to think about symmetry. If we've got more carbons than we have types of carbons, that means that there are multiple carbons that share the same environment. And that's something you often see when you have some kind of molecular symmetry. Like I said, we have 0 degrees of unsaturation. We've got one peak between 0 and 50. That's about at 18. That's probably a carbon single bonded to a carbon. And then we've got another carbon from 50 to 100, which is probably a carbon single bonded to an oxygen. This is diethyl ether. We have 2 identical carbons that are bonded to the O and 2 identical carbons that are only bonded to a C. If we looked at the proton spectrum, we would only see an ethyl group. Now that's useful because it's nice to know that we've got ethyl groups on here, but we would not see any specific indication how it's connected to an oxygen. We might be able to make that deduction, but it would certainly be nice to have this carbon-13 NMR spectrum alongside the proton spectrum for diethyl ether. Again, these methods are complementary. Neither one tells you the entire picture. Sometimes one is more useful than the other, but almost always they are most useful when used in conjunction with one another. Let's try this one. C4H6O4. So we've got 4 carbons. Again, we can get this from mass spec. 4 carbons, and we've got 4 peaks here. So each carbon is in a unique chemical environment. We can assume then that we have no molecular symmetry. If you calculate the degrees of unsaturation, it should be C4H10 if it was saturated. We have C4H6, which means we're missing 2 pairs of hydrogens. So this has a degree of unsaturation of 2. So we've got 2 double bonds or a double bond in a ring or something like that. But because we've only got 4 carbons, it's probably unlikely that we've got a ring. We've got a peak just above 50. This is actually at 52. That means that we are in carbon-oxygen single bond territory. We've got 2 peaks between 100 and 150. So again, those are carbon double bonded to carbon. And since those are right next to each other, they probably are in similar chemical environments. And therefore, we can probably assume that these 2 peaks are carbons that are double bonded to each other. And then we've got a peak at 168, which is going to be a carbon double bond O. Because it's so low, it's probably an ester or an acid. Ketones and aldehydes are the ones that show up at 200 and above. But as low as 160 is likely to be an ester or an acid. Now, if you put this structure together, this is what you get. This spectrum reflects what this structure is. Now, we said that this is an ester or an acid based on our location of our C double bond O peak. This is the ester. It's the C double bond O connected to an O connected to an R group. In this case, it's a methyl. So this is our carbon connected to a single bonded oxygen. That's our peak between 50 and 100. The reason I know this is not an acid and it has to be an ester is because we need a carbon single bonded to an O. There's got to be a carbon that can be single bonded to that oxygen specifically. If this methyl group, for example, was over on this carbon and we had an H on this O, making it a carboxylic acid, then we would not see a carbon single bonded to an O. This peak would move down, I would say up field, down in terms of ppm. But if we move this carbon over here, it would be single bonded to a carbon, so it would go down into the 0 to 50 range. So this peak right here, based on everything else that we know, tells me that this must be an ester and not an acid. So that's a very quick crash course on carbon-13 NMR. Again, it follows the same type of rules as hydrogen NMR does, except that we don't see splitting between carbons and hydrogens. We also don't see splitting between carbons and carbons. All that we can tell are the carbon environments that we have, and those environments tell us what the carbons are attached to, not really what they are next to, but rather what they are attached to. One topic that it very frequently shows up on the ACS final exam is a modification of carbon-13 NMR called DEPT, D-E-P-T, which stands for Distortionless Enhancement by Polarization Transfer. This is a type of what we call two-dimensional NMR. Now, what in the world does distortionless enhancement by polarization transfer stand for? Don't worry about what it stands for. Let's talk about what it does. This technique, DEPT or DEPT, is a technique that exploits the coupling constants between the carbons and the protons that they bear. Remember that carbons and the hydrogens that they have on them split with very large coupling constants. And for most simple carbon spectra, we use computers to ignore those splitting patterns. We just leave them out. But they can be exploited in certain ways that allow certain coupling constants to be selectively enhanced. We're going to use a series of pulses that are going to allow carbon with one hydrogen, or carbon with two hydrogens, or carbons with three hydrogens to be enhanced separately and selectively. The way this works is, as always, we pulse with our electromagnetic radiation, our radio signal, at 90 degrees from the axis of our magnetic field. And this will bump all of our nuclei out of the plane of the magnetic field, and they will cause them to precess like any other NMR active nuclei would. What makes DEPT different is that after a short delay, and the length of that delay will vary depending on the type of interaction that we want to enhance, we pulse another pulse of electromagnetic radiation at one of three specific angles. And the angle that we use, coupled with the time of delay that we pulse it after, will enhance these different types of couplings. Now here's how it works. C and H, like we talked about, have different gyromagnetic ratios, which means that they precess differently at different frequencies in a given magnetic field. That means that there will be a net magnetization that varies over time. Here's what I mean by that. Here's our magnetic field applied externally, our B0. Here's carbon-13 with its magnetic field. Here's hydrogen-1 with its magnetic field. But these precess at different rates in our magnet. Now, right now as drawn, they are both angled off to the side like this. So there is a net magnetization towards the left. They are pointing towards the left relative to our magnetic field. But hydrogen will precess faster than carbon-13. So a split second later, hydrogen will have precessed a little bit, but carbon-13 will have precessed less, or maybe not even at all. You can see now that the magnetization is less because we've got hydrogen no longer pointing off axis like carbon is. So whereas before we had more magnetization, then we have less magnetization. If hydrogen keeps on spinning, we're going to have magnetization that maybe they cancel each other out. Maybe hydrogen ends up pointing opposite of carbon-13 at some point. Eventually, carbon-13 is going to catch up, and its precession will start to come into effect too, to the point that now we've got maybe a little bit of magnetization towards the right. And as carbon-13 continues to rotate more, we get more net magnetization to the right. So as this proceeds, we're going to have magnetization to the right, then back to zero, then back to the left, then back to zero, then back to the left. That's going to alternate back and forth and back and forth and back and forth over time. Here I've plotted 3 graphs. Let's look at the blue line here. The blue line is the net magnetization over time for a carbon-13 bonded to a hydrogen, basically interacting with a hydrogen. That pattern you can see is a sine wave. It goes up and then back down and then back up. That magnetization plot is what we showed here. It's magnetized in one direction, and then it goes to zero, and then it magnetizes in the opposite direction, and then it goes back down to zero, then it magnetizes back in the other direction. It oscillates from one direction to the next. That is what the pattern looks like for a C and one H. It's a simple sine wave. But imagine that we put in another hydrogen that is also going to be precessing at the same rate as our first hydrogen is. In that case, the pattern of magnetization is going to be different, and that pattern is shown here in pink. It's still going to alternate. It's going to go up and then back down and then back up and then back down, but it's going to precess in a little bit of a different pattern. It's going to be 2 times sine times cosine. Don't worry about why that is, but just imagine that you're throwing in another variable for magnetization, and it ends up looking like the pink does. We can also throw in another hydrogen for CH3, and that's going to give us another pattern here, and that's in red, where it's going to magnetize up and then down and then up, and then it's going to magnetize to zero, and then it's going to go in the other direction, down and then back up to zero, and then back down and then back up to zero, and it's going to repeat in that pattern. So we've got 3 different types of alternating magnetization, and depending on which types of interactions are present, we will have access to these curves. Now, you notice that in the x-axis, here they are showing an angle, 0, 90, 180, 270, 300. This x-axis, you can think of it as 2 things. You can think of it as the time. So over time, we've got this alternating magnetization, but also you can think of it as the angle at which the magnetization is the greatest. For example, after this amount of time, after some period of time from here to here, the maximum magnetization for CH partners is at 90 degrees. They are magnetized 90 degrees from the axis of the external magnetic field. But for the CH2s and the CH3s, after that period of time, after our initial pulse, if you pulse at 90 degrees, there's no polarization there. There's no magnetization. So they will not show up on NMR after a X amount of time and a 90-degree pulse. But if we continue looking, if we look, say, at this period of time, we'll see magnetization for CH3s in red, for CH2s in pink, and for the CHs in blue. So they're all magnetized at, say, 45-degree angles after this amount of time. Only CH is magnetized at 90 degrees angle at this amount of time. After about 135 degrees and this amount of time at 135 degrees, our CH3s are highly magnetized, our CHs are somewhat magnetized, and our CH2s are highly magnetized, but in the opposite direction from these guys relative to the external magnetic field. So we've got this very specific combination of time and angle. And if we combine the two, we can look at different types of couplings in different ways. So again, at this point, our max magnetization for CH carbons is at 90. At this point, net magnetization will be 0 for CH3 and CH2. There'll be no signal. If we look here at 135, we have enhancement of the CH signals in blue and the CH3 signals in red, and we have magnetization of the CH2s in the opposite phase, so in the opposite direction relative to our B0. So we can break this up into 3 different time categories. After X amount of time, corresponding with 45 degree angles, at 2x amount of time, corresponding to 90 degree angles, and 3x amount of time, corresponding to 135 degree angles. If we pulse at 45 degrees, after X amount of time, all of our couplings will enhance. Their interactions with B0 will enhance. And we will see all 3 of them in our spectrum showing up after X amount of time if we pulse at 45 degree angle. If we pulse at 90 degrees after 2x amount of time, we will only see our CH couplings. And if we pulse at 135 degrees after 3x amount of time, we will only see our CH2s in the opposite direction of our CHs and our CH3s. So that probably sounds pretty complicated. Let me show you how we can use this to determine what a spectrum tells us about a structure. First, let's think about how depth 45, by that I mean depth being enhanced at 45 degree angle after X amount of time. The difference between depth 45 and a normal carbon-13 spectrum is that depth 45 enhances CH, CH2, and CH3. What it does not show is quaternary carbons. If there are carbons with no hydrogens, then their interactions will not show up in this spectrum. So depth 45, if we compare a depth 45 spectrum to a normal carbon-13 spectrum, any carbons that are quaternary will show up on the carbon-13 spectrum, but will be absent from the depth 45 spectrum, because what we are looking at in the depth 45 spectrum are the interactions between the carbons and their hydrogens. Here's an example of a depth experiment. Down here is a normal carbon-13 spectrum, and you can see it's a pretty complex spectrum. There's lots of peaks going on here. Now, fortunately, we don't need to worry about what this is. Our job is not to interpret the spectrum, but let's just look at what these different spectrums tell us. First of all, remember that carbon-13 NMR will show us all of our carbons. So these peaks are all of our carbons. If we compare carbon-13 to depth 45, meaning that we have pulsed at 45 degree angles after X amount of time to enhance all 3 of our types of couplings. Remember, after X amount of time and 45 degrees, all 3 of our coupling types are polarized, are magnetized. So you'll notice that the depth 45 looks exactly the same as our carbon-13. There are no peaks missing. That means that we have no quaternary carbons. No quaternary carbons in our spectrum, because if we did, they would not show up on depth 45. Okay, now here's depth 90, and let's look again at what depth 90 referred to. At 90 and 2x, we do not see our CH2s, nor do we see our CH3s. There's no net magnetization of those interactions. Only our CHs are magnetized at 90 degrees and 2x. So anything that's missing was a CH2 or a CH3. Only CHs will show up. So these peaks here, whatever these are, or those right there, those are CH2s and CH3s. The rest of these are CHs. Here's depth 135. Now remember, if we looked at what 135 was, after 3x time, our CHs and our CH3s are magnetized, but our CH2s are also magnetized, but they're magnetized in the opposite direction. So that means that these peaks here must be the CH2s. And this peak here, which was missing from our depth 90, therefore we know that was a CH3. This guy here was a CH3 because he shows up magnetized in a 135, but gone from a 90 and present in a 45. So by process of elimination, kind of by taking one spectrum and comparing it to the next, and comparing that spectrum to the next, and comparing that spectrum to the next, we can elucidate which types of peaks correspond to our signals on our spectrum. You can do a automated editing of a depth spectrum. We call that adept. Basically, that means that the corresponding peaks are subtracted from the previous spectrum. So we look at carbon-13 and we compare it to our depth 45 and we see that all of our peaks are there. Then we are going to subtract off the previous spectrum and we're only going to see our CH peaks. Those were these guys. Everything else disappeared. Then we're going to subtract off this spectrum from our depth 90, and that's only going to show us our CH2s. And then we're going to subtract that spectrum from our depth 135, and that's only going to show us our CH3s. Now, here they flipped this over. Remember that our CH2s would be inverted. So they inverted these peaks just so we could see everything up. That's what the adept editing does. Just there's no point in showing it inverted if it's the only peak there. If it's an adept, we know that those are our CH2s. Okay, let's practice. Let's try one. Let me show you how this works. Here's a difficult spectrum of a proton spectrum of a relatively simple molecule, C5H10O. We've only got 5 carbons. We've got 10 hydrogens, which means we've got 1 degree of unsaturation. We've got 1 oxygen. But holy moly, this is a difficult spectrum. We've got something that looks like an ethyl here. We've got a triplet here. So maybe that's an ethyl group. We've got a singlet here. We've got something weird going on around 5. That means we've probably got a double bond, but what does this mean? We've even got something crazy going on here around 5.75. This looks like maybe some doublets of triplets or some doublets of quartets or 2 doublets of doublets. So anyway, really weird spectrum going on here in the proton. But what we can do is we can use depth to really simplify this by looking at the carbons instead of the hydrogens. So here are the depth spectra from our molecule, from C5H10O that I just showed you. We've got proton decoupled carbon-13. That just means that the couplings between the protons and the hydrogens that would make our spectra very complicated have been removed. We call that carbon decoupled. So we've got carbon decoupled C13, and we see we've got 5 peaks. 1, 2, 3, 4, 5. So those are our 5 carbons. They are all in unique chemical environments, so we have no symmetry. We've got our depth 45. We'll talk about that in a minute. We've got our depth 90. We'll talk about that in a minute. And we've got our depth 135. Okay, so like I said, we've got 5 unique chemical environments. And let's remember what these ranges mean. From 0 to 50 should be a carbon that is single bonded to a carbon. From 50 to 100, we should have carbons that are single bonded to O's. And from 100 to 150, we should have carbons that are double bonded to carbons. We don't have anything beyond 150, which is why it's not on this graph. We don't have anything which is C double bonded to O. Now, if you think like a detective, our formula is C5H10O. We've only got one oxygen, which means that we've got two carbons bonded to the same oxygen. That sounds like an ether. Let's keep that in mind. The only way that we can have two carbons single bonded to an O with only one O is if it's an ether. So let's try to keep that in mind as we put this together. Let's compare our depth 45 to our carbon 13. Remember that depth 45 enhances CH, CH2, and CH3, but cannot amplify quaternary carbons because quaternary carbons do not have any hydrogens on them. So anything that does not show up in the depth 45 would be a quaternary carbon. We don't have anything missing from our depth 45. All of our peaks from our carbon 13 are present in our depth 45. So that just tells us we have no quaternary carbons. All right, depth 90 enhances our CH. Only our CHs are enhanced in depth 90. Again, I can show you that back in our plot here. At 90 degrees, after 2x amount of time, only our CH is enhanced. Our CH2s and CH3s show no amplification. Okay, so that CH is the one that's the most downfield. That's one of our C double bond Cs. That means that all of our other carbons are CH2s or CH3s. You see how this is getting easier to put together now. The next step is the 135. Now, like I said, these are only the opposing peaks. These are only the peaks that were opposite in magnetization. So these are our CH2s. We've filtered out the non-inverted ones. Okay, so we've got 3 CH2s, including one of the alkenes. This guy right here between 100 and 150 is a CH2 carbon double bonded to a carbon. So we've got a CH carbon double bonded to a carbon and a CH2 carbon double bonded to a carbon. We also have one of our C single bond O's, the 81 peak here. That C single bonded to an O was a CH2. And we've got our peak down here at about 35, which is our C single bonded to a C, was also a CH2. So if you put that together, we can determine then that the one peak remaining, the 59 ppm, which we haven't accounted for, is a CH3. That's what's left. That's the one thing we haven't accounted for. And that must be a CH3 on our O. So we've got a CH2 on the O. We've got a CH3 on an O. We've got a CH2 double bonded to a C and a C double bonded to a CH. Here's the structure that corresponds to our spectrum. And I've labeled the corresponding carbons on each graph. Let's start with our depth 90. Depth 90 will only show CH couplings. And we said that CH coupling is the most downfield, and it's going to be C double bond C. So that's carbon 1 right here. That's a C double bond to a C, and it's got one hydrogen on it. Okay, it's twin then. The other carbon that was double bonded was this guy here. That's our peak 2. And our peak 2 shows up in the depth 135, opposing only, which means that that's a CH2C. So that is a terminal alkene. Carbon 1 is a CH alkene. Carbon 2 is a CH2 alkene. So that's carbon 1 and carbon 2. Then we've got A CH3, that's the only one left over here, CH3, is our 5 carbon. He's single bonded to an O. That's going to be this guy here, CH3 single bonded to an O. We've also got carbon 4 was a CH2. These are all CH2s in the 135. The CH2, which is single bonded to an O. So that's that guy there. So there's our ether. And the one thing we have left over was our C that's only single bonded to other carbons. So that's got to be between carbon 1 and carbon 4. So that's how you read a depth spectrum. You'll be given 4 of these spectra, the regular carbon-13, depth 45, depth 90, depth 135. Your job is to know what each spectrum tells you and how to use different spectra in conjunction with one another to figure out what peaks are which. Notice that it was much easier to assemble this structure based on what the carbons were like rather than what the hydrogens were like. We thought we might have had an ethyl because we had this quartet here and a triplet here. We certainly did not have an ethyl in our structure. We thought we might have an alcohol because we've got this singlet between 2 and 5. We absolutely did not have an alcohol in our structure. We've got complex splitting from 5 to 6. We do have an alkene, but we've also got other things going on near 6 that looks even more complicated. So it's really difficult to interpret this from hydrogen, but it can be quite easy to interpret it from the depth. The last thing I want to mention is that there is something called two-dimensional spectroscopy. Now, I mentioned that depth is a type of 2D spectroscopy, but here's what a more traditional two-dimensional spectroscopy experiment looks like. This is what is called a hydrogen-to-hydrogen homonuclear two-dimensional spectrum. And this type of spectroscopy is called correlation spectroscopy. It's abbreviated COSY. I'm going to show you on the next slide. All of these 2D methods have really fun names. They call this COSY, correlation spectroscopy. But if you look at what this spectrum is, you can see that we've got a proton spectrum on the x-axis here from 0 up to about 10 ppm. And then we've got the same spectrum on the y-axis, also from 0 ppm all the way up to about 10 ppm. So we've got the proton NMR spectrum graphed against the same proton NMR spectrum. And what we care about in 2D spectroscopy are where these different points intersect. Now notice that we've got a diagonal here, that we've got all these signals on the diagonal from our spectrum over here, crosses with 5 from our spectrum over here, we get a signal. Where 1 over here crosses with 1 over here, we get a signal. That simply means that the hydrogens related to the signal on the 5 are related to the hydrogens that are on the signal on the 5. That's not surprising. So all of our correlation we see in the diagonal, we can ignore. That's obvious. But it's the off-axis things that are interesting. For example, see this signal here in A. Our A signal is relating whatever hydrogens are causing signal 1 and whatever hydrogens are causing signal 2. That means that the hydrogens that are causing signal 1 and the hydrogens that are causing signal 2 are related to one another. We kind of saw this with the roofing effect in proton NMR, that 2 peaks that were related would lean into one another. But if you look at it from a 2D perspective, we can very clearly see that 1 and 2 are related. That is here. Here's carbon 1, here's carbon 2. They are related. If you didn't look at that, if you didn't look at the 2D spectrum, it might not be obvious that 1 and 2 are next to each other. But looking at the 2D, it is patently obvious that they are next to each other. Same thing with here's point B. 4 and 5 are correlated. 4 and 5 are correlated. So we know 1 and 2 are next to each other. That's obvious. We know 4 and 5 are next to each other. That are obvious. But here's C. C is very interesting. 1 and 3 appear to be correlated. Why would that be? Why would 1 and 3 be correlated? Well, it's because of the geometry of that double bond. The hydrogen on 3 is able to interact with the hydrogens on 1 because they are very near each other in space. Remember, we said when we looked at coupling in proton NMR that hydrogens have to be neighboring through bonding, unless they are somewhat or somehow positioned very near each other in space due to a rigid structure. Well, a pi bond is a rigid structure, and no matter how the other sigma bonds rotate, the hydrogens on carbon 1 and the hydrogen on carbon 3 are always going to be in a certain proximity to one another. So 1 and 3 will be correlated, but notice they'll only be correlated if it's a trans double bond. Notice that if it was a cis double bond and the methyl carbon 1 was pointing up above the 2 like that, then the 1s would be nowhere near the 3 in space, and there would be no correlation from 1 to 3. So specifically here, the signal for C tells us that 1 and 3 are correlated, and it's likely to be a double bond that puts them near each other. And in this case, we need a trans double bond to put them near each other. There's also correlation from 2 to 3. That's not surprising. 2 and 3 are correlated. Hydrogen on 2 and hydrogen on 3, they are splitting with each other over a trans double bond. So that would be, say, a doublet with a splitting constant of about 15 hertz. So those are correlated as well. We can also see 2 and 3 over here. That's obvious. If 3 and 2 are correlated, 2 and 3 are correlated. So across the diagonal, you're going to see the same patterns. B over here, 4 to 5, is same thing over here, B from 4 to 5. So that's all I wanted to show you about 2D NMR. 2D NMR will not be on the ACS final. I'm not going to examine you on it. I just wanted you to be introduced to that notion that there are ways to further probe how two hydrogens are related to one another, either through bonding or through space. Here are some of the terms of other types of 2D spectra, and I've grouped them based on how they relate to different types of hydrogens. So homonuclear through bond correlation methods, meaning we're looking at the same type of nucleus, for example, hydrogen to hydrogen, and we are looking at how they interact through bonding. So we saw correlation spectroscopy. That's what I just showed you. There's another method called exclusive correlation spectroscopy, which instead of COSY, they call it eCOSY. There's another type called total correlation spectroscopy, which they call TOCSY. My favorite one is incredible natural abundance double quantum transfer experiment, which they call inadequate. INADEQT transfer, okay. Incredible natural abundance double quantum transfer experiment. Then we have heteronuclear geminal correlation method. So two nuclei that are two different types of nuclei, so carbon to hydrogen, for example, that are related geminally, so they're connected to each other. That's what we saw for DEPT. In DEPT, we were looking at carbons that had one hydrogen, carbons that had two hydrogens, carbons that had three hydrogens, and how they were differently polarized. So that was distortionless enhancement by polarization transfer, or DEPT. There's also insensitive nuclei enhanced by polarization transfer, which they call INEPT. Then there's heteronuclear through bond correlation method. So instead of homonuclear, it's heteronuclear through bond. So there's heteronuclear single quantum correlation spectroscopy, or HSQC, heteronuclear multiple bond correlation spectroscopy, HMBC. Those aren't too fun. Then you've got through space correlation methods. So there's also ways to have or exploit the interaction of nuclei through space rather than through bonding. One of those is called nuclear Overhauser effect spectroscopy, or NOSI, or rotating frame nuclear Overhauser effect spectroscopy, or ROSI. So we've got COSY, we've got toxy, we've got inadequate, we've got dept and inept, we've got nosies and rosies, and ecosies. We've got all kinds of fun methods. So that's it for carbon-13, dept, and 2D NMR. We can continue doing any NMR related topics in workshop, whatever you determine would be most useful.